Or then let's just, yeah. So thank you guys for coming. I'm Maisam Naji, and I'm presenting this paper with Abdulhamid Dabbousi. So we decided to take this paper titled Fast Online Object Tracking and Segmentation and Unifying Approach. And for several reasons, we chose this paper, as you will see later in this presentation. So object tracking is a fundamental task in various video applications, and hence it's a very interesting task and a process. And online tracking itself is especially forgotten just because when you say online tracking, it means two things. It's live tracking and the frames per sec. Sorry, the tracking or the processing is being used on is around, I think, 34 frames per sec, right? Abdulhamid?
Yeah.
Yeah. So this is the natural and the normal frames per sec. And also it means that the network does not see, the model does not see the future frames to be able to, it does not see the future frames and does not include it in its calculations. So it just works with what it sees at the moment. VOT, video object tracking with boundaries, is a much easier task than video object segmentation normally. And VOS, of course, is way more expensive computationally and requires much, and its accuracy generally is not as good. However, in this paper, they actually reduce the gap between these two, between VOT and VOS, and at the same time they do the two processings. Can you move to the next slide?
Mm-hmm.
Do you want to talk about this, Abdulhamid?
Yeah, sure. So the technology they came up with, they called SIAM mask, and it is motivated by convolutional neural networks that are known as Siamese networks. This particular network was trained on millions of video frames, and it primarily attempted to learn 3 separate tasks and to use these 3 tasks in its identification process. The first is the similarity between a target object and a candidate object. So what it does is it basically it takes a target object from the current frame and it tries to see how similar it is to the target object it had been tracking in previous frames. And by doing so, it tells whether this current object is the same as the old object. Another task it tried to do was the very common bounding box regression, where you try to maintain a bounding box around your target object throughout the whole video. And the final one is a class agnostic binary segmentation. And what this does is it's basically a mask for every pixel of the frame, and it does an identification. It changes it into an identification problem, and it tries to tell whether this pixel belongs to the object it originally was trying to track or not. This network is basically a convolutional network, and these 3 tasks, their results, their predictions are all fed into the same loss function for the final result. This is what the architecture looks like, and a very important thing this paper stresses on multiple times is how simple it is. It really is a very simplistic approach, and because of its simplicity, it was able to reach the online tracking ability. So I will go over this architecture in the next slide, but for now, because it's quite large, this would be known as your candidate object or candidate picture. The bottom one is your original picture, and it's a window from that picture. So they use a sliding window over the whole frame. Those are the convolutional networks. This is the convolution. This is the result. This is their mask. This is the original bounding box problem, and this is the similarity score problem. So as you could see at the very beginning, you have an exemplar image Z, and then an nth candidate from a window of the image X. And what you do is sliding over sliding a window over the image X, you perform a convolution for every part to check the similarities between your target object over here and then your candidate, your original object. The similarity, they denote the similarity of every candidate window as this, and this would be basically the result of this operation right here. So what they end up with is an image where they have a high probability of where the object is currently sitting at. For the original two tasks, the box problem and the score problem, they use the previously known methods SIAM-FC and SIAM-RPN to find the boxes and the similarity scores respectively. And those are, those are old, and they just use those alongside their own network, which is at the very top. It's H5, and H5 basically gets fed the convolution result, and it produces a mask. Again, what a binary mask is an identification for every pixel. It classifies every pixel, whether it belongs to the original object or not. And over here, you could see in the result, you have an image of this bird. This is what the mask would look like afterwards. The white parts are where it belongs to. And then due to the box, you could see a boxing frame around it. This neural network, the reason they say it's a very simple approach is because this is only a 2-layer, 1-by-1 convolutional neural network. But what matters is the number of channels. The first layer has 256 channels, and the final layer has 4,000 channels. And what this allows the network to do is to distinguish between your current item and what they call as distractors. So if you look at the big window over here, you could see this is our target bird, and these are other birds that look very similar, and those are known as distractors. And by increasing the number of channels for every convolutional layer, they're able to distinguish between the correct object and the distractors. And at the very bottom, you could also see the loss function they use. The first one is the loss function they use purely for their neural network, for their convolutional network, and then they feed its result along with the result of the SIAM-FC and SIAM-RPN, which are the score and the boxes, into the final loss function, which is used at the very end for classification. Mason?
Yes. Yeah. So so after Abdelhamid just covered now the architecture. So what these guys did, they wanted to try to experiment on some benchmarks for VOT, video object tracking, and they used VOT 2018, and this paper was published 2019. The metric they used mean intersection over union and average precision. As well, they worked with Davis 2016 and 2017 YouTube VOS as benchmarks for their VOS measurements. Can you move to the next slide so we can discuss the table? Okay, so here you see some other approaches, some other works that has been done, and also they have their different masking precision and accuracy. And we can see that, okay, some other approaches could reach higher, I mean, much higher percentage when it comes to average precision and mean intersection over union. However, what is really important about this publication itself is the fact that it could increase, it could achieve such an accuracy with also maintaining a high frame per second. And in this chart here, yes, you can see that most of maybe the highest approaches, you can say it was, I'm assuming this is 8 frames per second, which is very limiting to work with in an online application, right? However, their approach itself can go, I think, as around 55 frames per second with maintaining 75% accuracy, mean intersection over union. Now, this is some really nice results that these guys were sharing in their paper and on their project website. So you see that it works pretty well for multiple objects too. And if you notice, for example, in the pigs line row down, you can see that even if there is a third object intersecting with a second object, it still segments these three objects without with understanding, with a good understanding of okay, what did the previous frames information get and how does it change throughout time. Can we move a bit, one more, Abdulhamid? So this is a real-time demo of how does it work. So yeah, so as you see it's a semi-supervised approach where where the user, or in this case, like the demo user, has to identify the location of the object, and then it will learn how to use it. Now, this network has been trained over, I think, how many videos? 40 million?
It's in the millions of frames, yes.
Yeah, millions of frames of videos. So it has a set of object that is really good at detecting. Can you move to the next frame? Slide. Yeah. So you see, even this is now slowed down for a better understanding of what's happening. You see, like within the change, even if the perspective angle changes, it still maintains a pretty good segmentation and tracking at the same time. If you want, if you want to check really quick before you go to that slide, we can also open the link. This link, it has a collection of really nice. Can you skip to the maybe the octopus one or? Okay.
So this is basically it for the presentation. Again, the contribution of this paper to the world of image tracking and segmentation of inside a video is twofolded. First, it narrows the gap between video object targeting and video object segmentation, and it allows you to do both, where you get both a bounding box and a mask. And the other very important contribution is how simple the result is. It just uses a two-layered neural network, and it is able to achieve online classification, again, where it's in real time without having access to future frames. And that was basically it. That's your presentation from myself and Maysam Naji.